Hi, physical science. It's good to see you again. It's April 1st, and it's no Fool's Day. This is for real. And I'd like to talk to you today about Pascal's principle and pressure. I'm on page 442. So stop the recording, go get your book. You should have it already anyway. Page 442. So you're back. Blaise Pascal was in the 1600s, Frenchman, and he said that if you press your toothpaste tube down here, it feels that pressure everywhere, every direction on the toothpaste tube, even out the top. And so that's why the toothpaste comes out there. It's because you're pressing down here. This fluid in the inside is not compressible. And so whenever you put pressure down here, it feels the pressure up there and squirts it out the top. The best way I can illustrate that is what I call my Cartesian diver. And I took a test tube, I put a little balloon piece on the top, put a little water in it, not entirely full, and I put a rubber band around it, and I put it inside of this 2-liter bottle. Screwed the cap on, and here's what happens. Let's see if you can see this. That's the bottom of the test tube. When I squeeze on it right here, it goes down. When I let off, it goes back up. Now let's take a look at the bottom underneath. And here comes my little test tube. And if you look at it right, if I can get it to where you can see it. And you see my little test tube right there. Let's see if I can go a different direction with this. Little test tube right there. That's where the balloon is over the top of the test tube. When I squeeze it down here, watch the balloon cave in. Cave in, cave in, cave in, cave in, cave in, cave in. So whatever pressure you put anywhere on a confined fluid, it feels that pressure throughout all of the fluid, including the top of this test tube where the balloon is, and it caves it in. When it caves it in, since water is not compressible, it shoves the water up the test tube further, and you see that air pocket that's right there? It becomes smaller. It's like taking part of your life preserver and cutting it in half and throwing it away. That's not enough life preserver to hold you. So you go down. So I'm going to squeeze on the side again. You can watch that test tube go down. Boom, there it goes. Because that life preserver got smaller. When I release it, that life preserver gets bigger again. And the air expands in there and the water comes down the bottom of that. Okay, so that's a really good demonstration of Pascal's principle. Now, in order to understand what Pascal's principle is talking about, you have to understand pressure. And on page 443, we have a discussion on pressure. Pressure is force exerted per unit area. What do you mean? Well, if I weigh 160 pounds, which I do, and I have feet that are hitting the floor, and my feet, see if I can get it up there. My feet have a length of about 10 inches and a width of about 4 inches. Let's see if I can let you see that. There we go. 4 inches. So what's 10 times 4? Is that 40? And is there another foot over here? Is that 80? So you've got 80 square inches. And so the pressure that is felt on the floor due to me standing on the floor is 160 divided by 80, or 2 PSI, pounds per That's what the division bar means in science class, per. Pounds per square inch. PSI, that's what it stands for. And I have about 2 PSI of pressure on the floor right now. Well, what happens if I stand on 1 foot? If I stand on 1 foot, then this thing cuts down to 40. And 160 divided by 40 is 4. So if the area that I'm standing on gets smaller and the force remains the same, the pressure goes up. What do you mean? Well, let's see, the force remained the same, but the area went from 80 down to 40, so it got bigger pressure because these are inversely related. Pressure and area are inversely related. As one goes up, the other goes down. As one goes down, the other one goes up. But pressure and force are directly related. Bigger force, that is, if I get a big fat belly, then I'm going to have more pressure on the floor. That number is going to go up. Okay? Now, pressures that we use are not PSI. That's an English unit. So in the metric system or Systems International, we go like this. Pressure is force in newtons divided by area in square meters. And this is measured in pascals for Blaise Pascal. So therefore, 1 Pascal of pressure is equal to 1 Newton exerted over a force of 1 square meter. And so what is a Newton? A Newton is about as much force as you feel from the weight you feel on your hand with a 100-gram mass, which is about 1/4 of a pound. Okay, and let's spread that over a square meter of area. Now this board right here is not a meter high. A meter high would be 2 of these boards high and 1 wide. So it's an area about there to there to there to there. And let's take this and let's spread this over that entire area. If you did that, you'd have to take your knife and you'd have to make it into shavings to spread it over that big of an area. And with any little shaving, it's almost like dust on that big of a surface. Does it feel any appreciable pressure? Any part of that surface, if you have this thing cut down to dust and spread it over the top of that? No. So a Pascal of pressure is a very small unit of pressure. So in the laboratory, we use kilopascals. 1 kilo of pascals, little k, big P, little a. 1 kilo of pascals is 1,000 pascals. Okay. So now I've given you some definitions. We'll work the problems in our next lesson. But let me show you one more demonstration. By the way, I'll talk about that atmospheric pressure. Okay, one more demonstration is, I said, if the area goes down, the ultimate pressure goes up. So when I lift my foot, I'm exerting more pressure. Ice skates are honed down to a very fine blade because when you put more pressure on ice, it melts. It works just the opposite of any other substance. When you put pressure on it, it doesn't squeeze the solid into a tighter solid. It basically opens it up to a liquid. And that's an odd thing. God made it that way so that ice would float on top of water. It's really neat. Anyway, so it melts and therefore it reduces friction so the ice skater can go faster. That's why they sharpen their blades, because they want to make the area underneath their blade smaller so the pressure is greater so that the ice melts. Okay, and in this demonstration, I'll have to show you that tomorrow because I just ran out of time. See ya. Do the quiz.